Find the volume of the solid enclosed by the parabolic cylinder y is equal to x squared and the planes z equals 3y and z equals 2y. So graphically, the parabolic cylinder z is equal to 3y. The parabolic cylinder y is equal to x squared extends along the z-axis. I have a plane that goes through z is equal to 3y, and then I have a plane that's shifted up 2 units along the z-axis. So the plane that goes through z equals 2 plus y is higher than the plane z is equal to 3y. Then on y is equal to x squared, y is equal to x squared is this parabola. If that's 1, if that's negative 1, y is equal to 1 would be that region here. If I integrate dy dx, so from the bottom up, so this is x, this is y. To find the intersection, or to find the region of integration, I need to find out where the two planes intersect. So I'm looking for where z is equal to 3y and z is equal to 2 plus y intersect. If I solve this system of equations, I get 3y is equal to 2 plus y. So 2y is equal to 2, which means y is equal to 1. So y is equal to 1 is this horizontal line here. When y is equal to 1, z is equal to 3, and z is also equal to 3 here. So that's the intersection point. And by finding where y solves this system, I'm able to generate the region in which I'm integrating over. So the volume is equal to the double integral. Z is equal to 2 plus y is this plane up here. Z is equal to 3y is this plane here. So where these intersect along this region is going to be the top plane, which is 2 plus y, minus the bottom plane, which is 3y. So just like areas in Calc 1, it's top minus bottom. Same thing with these, top minus bottom. I'm integrating with respect to y, and then with respect to x. So with respect to y, I start off on this curve, which is x squared. I end at 1. So my bounds of integration with respect to y are from x squared to 1. My x goes from negative 1 to positive 1. So negative 1 to positive 1, which is equal to the integral from negative 1 to 1, then the integral from x squared to 1. If I simplify this inside, this turns into 2 minus 2y dy dx. Once you integrate this is equal to 16/15. Example. Sketch the region of integration and change the order of integration for -2 to 2, 0 to the square root of 4 minus y squared, f of xy dx dy. So on this double integral, x goes from 0 to the square root of 4 minus y squared. And y goes from -2 to +2. So if I focus on x is less than or equal to this root, if I set that equal, x is equal to the square root of 4 minus y squared. If I square both sides, x squared is equal to 4 minus y squared. If I add y squared to both sides, I get x squared plus y squared is equal to 4. This is a circle centered at the origin with the radius of 2. Since this is the positive root only, I'm looking for where the x's are positive. So x's are positive in the right half of that circle centered at the origin with the radius of 2. Y goes from -2 to +2. So this is my region. Since I want to change the order of integration, I want dy dx, so I want y to go from this bottom upward, and I'm going to keep the x constant. So if I have this equation, I want to solve for y. So y squared is equal to 4 minus x squared. So y is equal to plus or minus the square root of 4 minus x squared. So this bottom portion is negative root 4 minus x squared. This upper portion is positive root 4 minus x squared. So this double integral can be rewritten as f of xy dy dx, where y goes from negative root 4 minus x squared to positive root 4 minus x squared, and now x goes from 0 to 2. This x value is 2. So x ranges from 0 to 2. example. Instead of find, let's say setup. Setup the double integral to find the volume of the solid bounded by the graphs of the equations z is equal to x squared plus y squared and z is equal to 18 minus x squared minus y squared. So graphically, z is equal to x squared plus y squared is an elliptic paraboloid. Which is this. Z is equal to 18 minus x squared minus y squared is an elliptic paraboloid shifted up 18 units but upside down. So shifted up 18 units and then flipped upside down. So I'm looking for the volume of this region here, which looks like an egg. If I project this into the XY plane to determine what the region D is, that's the region D. So let's determine where these two paraboloids intersect. To find the intersection points, I'm going to set the z values equal. So x squared plus y squared is equal to 18 minus x squared minus y squared. If I move the x squareds and y squareds to the left side, I end up with 2x squared plus 2y squared is equal to 18. If I divide both sides by 2, x squared plus y squared is equal to 9, which is a circle centered at the origin with the radius of 3. So the region that I'm integrating over is this here. Let's integrate dy dx, which means y goes from this lower value to this upper value. If I solve for y, this upper curve is y is equal to the square root of 9 minus x squared. this lower curve is y is equal to negative root 9 minus x squared. So the volume of that region is equal to the integral, the double integral of the top function or the top curve minus the bottom curve. The curve on top is 18 minus x squared minus y squared minus the curve on the bottom. The curve on the bottom is this x squared plus y squared. I'm integrating with respect to y first, and then with respect to x. Y goes from this lower curve to this upper curve. So this is x, this is y. This volume projected onto the xy plane will result in this. So y goes from negative root 9 minus x squared to positive root 9 minus x squared. X goes from, this point is negative 3 and this point is 3. Since this is a circle centered at the origin with the radius of 3. So all of these are 3 units from the origin. So bounds of integration for x are from negative 3 to positive 3. If I simplify this integral, I'm integrating from negative 3 to 3, and then negative root 9 minus x squared to positive root 9 minus x squared of 18 minus 2x squared minus 2y squared dy dx.